Section: Introduction. In this section, we introduce how to evaluate the ability of models to correct their course using our benchmark, C-EVAL. We created C-EVAL by selecting 500 pairs of harmful requests and their corresponding harmful responses from the PKU SAFE RLHF dataset, which originally contained over 83,000 preference entries for reinforcement learning from human feedback. We specifically chose entries related to safety where the response was longer than 80 tokens. For more details, we refer to the appendix. The overall approach of C-EVAL is illustrated in a figure. To observe potential course correction behavior, we start with an initial harmful response, which we call the initial harmful response, derived from the corresponding harmful response. We also include specific markers between the harmful request and the initial harmful response to indicate that the initial harmful response was generated by the model itself, not the user. Our evaluation focuses on open-source models because many closed models, like GPT-4, do not allow us to control these markers. In the second phase of our evaluation, we sample multiple response paths based on the input of the harmful request and the initial harmful response. We then measure how many of these paths show corrective behavior. To accurately detect course correction, we prompt a language model. We define a metric to quantify the course correction performance for a given input, which calculates the ratio of corrected paths to the total number of sampled paths. For C-EVAL, we report two metrics: one that examines how the amount of harmful content generated affects the model's ability to correct itself, and another that provides a simple average for overall assessment. Section Summary. In this section, we introduce the C-EVAL benchmark, designed to quantitatively assess the course correction abilities of open-source large language models, LLMs, in response to harmful content. By analyzing 500 harmful request and response pairs, we establish metrics to evaluate how effectively these models can redirect harmful outputs, highlighting significant variations in their performance. Section: Evaluation with C-EVAL. In this section, we apply the C-EVAL benchmark to explore how effectively large language models, LLMs, can correct themselves after initially providing harmful responses. Model selection. We evaluate 10 advanced open-source LLMs, including LLAMA2 CHAT7B, Vicuña version 1.57b, Phi3 small, ZEPHYR7b, LLAMA3INSTRUCT8b, CHATGLM49b, and various sizes of Qwen2, 0.5b, 1.5b, 7b, and 72b. These models are current and have mostly undergone safety tuning processes like supervised fine-tuning and reinforcement learning from human feedback, except for Vicuña version 1.5, which only received supervised fine-tuning based on shared GPT user conversations without specific safety data. We provide details about the model sizes and safety tuning methods in a table. Results. We use two metrics, core at K and mean core, with a sample size of 20 to explore different response paths and a measure of 32 to assess timely corrections. For clarity, we convert the scores into a percentage format ranging from 0 to 100%. We evaluate the selected LLMs using the complete C-EVAL dataset, and the overall results are summarized in a table. We also illustrate the variation in core at K across different K values in a figure, showing how the length of the initial harmful response affects the model's ability to correct themselves. Findings. We summarize our key findings as follows. 1. Performance disparity. There is a significant difference in course correction abilities among the models we evaluated. Notably, LLAMA3INSTRUCT and Phi3 small achieve mean core scores around 90%, while 4 other models perform poorly, with mean core scores below 20%, indicating a clear divide in their correction capabilities. 2. Scaling trends. Larger models do not always outperform smaller ones, as performance does not consistently improve with increased model size. For instance, the 7B version of Qwen2 shows markedly different performance compared to other models of varying sizes within the same family. 3. Impact of harmful content length. For some models, longer harmful responses make it more challenging for them to correct themselves, aligning with recent research on model alignment. However, there are exceptions, such as LLAMA2 and Vicuña version 1.5, which initially show a decline in performance but then improve. This could be due to two reasons. 1. As harmful content increases, the model gathers more contextual information, enhancing its ability to identify mistakes and make corrections. 2. Some models may issue corrections or warnings only after presenting harmful content. This delayed correction is typically not captured in our setup with a measure of 32. We further support our hypotheses in the appendix, and due to space constraints, we reserve additional analysis and case studies for that section. C-SYN, a synthetic dataset for preference learning. In this section, we outline how we created C-SYN, a synthetic dataset containing 750,000 entries designed to teach the importance of timely course correction. Principles and practices. To align the model with human values, we establish two key principles. We then generate responses that are ranked based on how well they adhere to these principles, reflecting their alignment with human values. Value principles. We define two main principles. 1. Course correction is preferable to inaction. Responses that clearly attempt to correct mistakes are rated higher than those that do not. 2. Early corrections are favored. Responses that address harmful behaviors sooner are preferred over those that correct later, emphasizing the need for prompt intervention to ensure safe interactions. Additionally, we maintain a fundamental principle. Responses that are completely safe in response to harmful requests are always the most preferred. By following these principles, we create responses that embody these values. Practices. Similar to our approach in creating C-EVAL, we start with 50,000 pairs of harmful and follow-up responses selected from PKU Safe RLHF. For each harmful response, we gather 6 ranked responses based on our value principles. Inspired by the C-EVAL methodology, we generate corrective responses by truncating the follow-up responses at natural linguistic breaks, specifically at punctuation marks that occur roughly every fifth of the way through the follow-up response. This method allows us to create 4 initial harmful responses of varying lengths without arbitrary cutoffs. Using these initial responses, we find that with a well-aligned LLM, such as LLAMA2 we can generate contextually appropriate course correction continuations. We do this by adding a simple corrective trigger immediately after the harmful content. For example, a trigger like, "However, I cannot provide," can effectively prompt the LLM to take a corrective approach. To avoid the risk of reward hacking, we randomly select a trigger from a predefined set, ensuring variability and preventing dependence on a single trigger. For each harmful response, we also collect a safe response by prompting the aligned model. Thus, we end up with 6 ranked responses: the 4 synthetic responses, the follow-up response, and the safe response. The preferences among these responses are illustrated in a figure. By pairing these responses, we create a total of 15 pairs of preference data for each harmful response, resulting in a final dataset of C-SYN with 750,000 entries. Formalized data synthesizing algorithm. To clarify, we organize the data synthesis process in an algorithm, where preferred responses are denoted as R+ and non-preferred responses as R-. Section Summary. In this section, we evaluate the course correction capabilities of 10 state-of-the-art open-source LLMs using the C-EVAL benchmark, revealing significant performance disparities where LLAMA3 INSTRUCT and Phi3 small excel, while some models struggle with longer harmful responses. Additionally, we introduce C-SYN, a synthetic dataset of 750,000 entries designed to teach timely course correction, emphasizing the importance of early and effective responses to harmful content. Section: Quality Examination. In this section, we examine the quality of the responses generated by the large language model, LLM, through a human evaluation. Our goal is to determine how reliable the model is in producing responses that correct previous mistakes. To do this, we enlisted 3 annotators to evaluate 200 responses from the model we aligned. The evaluation showed a success rate of 98%, and we found a strong agreement among the annotators, with a score of 0.79, indicating that our approach is effective. These findings support the idea that well-aligned LLMs can be used to create useful synthetic data. More details can be found in the appendix. Next, we explore how to use C-SYN to give course correction abilities to 2 LLMs, LLAMA2CHAT7B and QWEN27B. For our alignment algorithm, we chose the standard direct preference optimization (DPO) method. In this context, the loss function for DPO helps us optimize the model's policy, comparing it to a reference policy. Our dataset consists of pairs of preferences, where we have a prompt and 2 responses, one preferred and one not preferred. We calculate the expected value over the dataset, applying the logarithm of the sigmoid function to the difference in log probabilities, adjusted by a temperature parameter that controls how sensitive the model is to preferences. In our experimental setup, we set the temperature parameter to 1 and the learning rate to 5 millionths. We trained the models for 3 epochs using a batch size of 256. Our experiments are designed to answer 4 key research questions, demonstrating the effectiveness of C-SYN. 1. Does preference learning improve the ILM's ability to correct mistakes? 2. Does learning to correct mistakes negatively impact overall performance? 3. Does learning to correct mistakes make LLMs more resilient to jailbreak attacks? 4. How well does C-SYN transfer to improve LLMs that are out of distribution? To address these questions, we will test the trained LLM on a specific evaluation set for the first question. The second question will be examined using well-known performance and safety metrics, with 8 benchmarks selected for this purpose. For the third question, we will apply several recognized jailbreak attack methods. Finally, for the fourth question, we will apply C-SYN, which was developed using the Llama Chat 7B model, to the QWEN27B model, which has a different distribution. More details are available in the appendix. Our results, which are summarized in tables, show the performance of the models in safety-related evaluations and general benchmarks. We also provide examples of the responses from the trained models. Regarding the first question, training with C-SYN significantly improves the course correction abilities of both models, especially for Llama Chat 7B, which initially struggled in this area. For the second question, we found that the performance of the trained models remained consistent across various benchmarks compared to the untuned versions, with only a slight decline of less than 1%. Additionally, we observed a small improvement in safety metrics, likely due to the alignment training enhancing the model's overall safety. For the third question, our results indicate that the models have become more resilient to jailbreak attacks, as shown by a decrease in the attack success rate for all 4 types of attacks we tested. This suggests that enhancing the model's ability to correct itself can also improve its resistance to safety threats. Finally, for the fourth question, the results with QWEN27B confirm that C-SYN, derived from Llama Chat, effectively boosts the performance of out-of-distribution LLMs, indicating its potential for broader applications across different models. We also analyze the token-level dynamics to see if our method improves the model's course correction capability by looking at the distribution of safety tokens. While these tokens are not perfect indicators of corrective behavior, they do provide some insight into the model's tendency to self-correct during the decoding process. Our analysis shows that our method increases the overall probability of safety tokens at various decoding positions, particularly noticeable in later stages. We averaged the distribution of LLAMA2CHAT7B across 20 harmful prompts for this analysis. For further details and additional experiments, please refer to the appendix. Section Summary. In this section, we evaluate the quality of LLM-generated responses through human assessment, achieving a 98% success rate and strong inter-annotator agreement, which supports the use of aligned LLMs for synthetic data generation. We also explore the effectiveness of C-SYN in enhancing course correction capabilities in two LLMs, demonstrating improvements in performance, safety, and resilience against jailbreak attacks, while confirming the method's transferability to out-of-distribution models. Section: Related work. In this section, we discuss the safety of large language models, LLMs, and the importance of red teaming. As LLMs are increasingly used in real-world applications, ensuring their safety has become a crucial focus. One effective method for evaluating the safety of these models is red teaming, which involves intentionally challenging the models with difficult and potentially harmful inputs to identify their weaknesses and failure points. A key technique in red teaming is the jailbreak attack, where we create algorithms that lead the models, especially those designed with safety features, outside their protective boundaries. Many notable jailbreak attacks look for prompts that prompt an initial positive response from the model, such as saying, "Sure, I am happy to help you with that." The idea is that if the model starts with such an affirmation, it is more likely to continue fulfilling the harmful request. To counteract the challenges posed by jailbreak attacks, we can use course correction, which helps steer the models back on track instead of allowing them to generate harmful content. This method offers flexible protection and improves resilience against sophisticated attacks. Next, we explore alignment approaches in AI, which aim to ensure that AI models behave in ways that align with human values and intentions, making them user-friendly and safe. We can categorize alignment approaches based on whether they involve reinforcement learning, RL. In RL methods, advanced chat LLMs are fine-tuned using reinforcement learning from human feedback, RLHF, which adjusts a reward model to match human preferences and optimizes the LLM to maximize rewards using algorithms like proximal policy optimization, PPO. Additionally, RLAIF uses feedback from AI instead of humans to train the reward model. Non-RL alignment methods can be split into those that require learning, like supervised fine-tuning, SFT, and those that do not. Some learning-based algorithms, such as direct preference optimization, DPO, and reward reinforcement from human feedback, RRHF, avoid the instability often found in RL algorithms. There are also approaches like RAIN and URAIL that do not require any training, but these can lead to extra costs in terms of time or resources, making them less practical for industrial use. Our work stands out because we use fully synthetic preference data. Unlike RLAIF, which relies on AI models for preference labeling, we create preference samples based on human values, ensuring that our preferences are self-contained. We also address a limitation in the evaluation protocol of C-EVAL. We simulate the initial phase of harmful content generation by directly prompting the LLM with a shortened harmful response that follows the user prompt. However, since this simulated harmful content comes from the PKU-safe RLHF dataset rather than being generated by the model we are testing, there is an inherent bias. The bias increases as the distribution of the tested model diverges from that of llama, which generates the harmful responses. Fortunately, we can easily fix this limitation by gathering relevant harmful responses for each model before evaluation. This can be done by first conducting a jailbreak attack on the test model using requests from C-EVAL. However, to keep C-EVAL user-friendly, we have chosen not to implement this dynamic evaluation strategy and have maintained the current version. Furthermore, the synthetic dataset we have created meets the standards for preference learning datasets, making it suitable for various alignment algorithms that optimize models based on pairwise preferences. In our research, we have chosen to use DPO because it is stable and requires less memory during training compared to the PPO algorithm used in traditional RLHF methods. However, this choice does not mean that DPO is the best algorithm. We need further experiments to fully assess its effectiveness and to explore other potential algorithms. We also recognize that there may be specific optimizations or new alignment algorithms designed for course correction tasks. However, our research primarily focuses on addressing the problem through the patterns in training data, which may not fully capture these potential advancements. We also examine the relationship between course correction and superficial alignment. The limited ability of current models to perform course correction indicates a superficial alignment with safety standards. Recent studies have shown that the distribution of tokens varies across different positions in the decoding process, suggesting different levels of safety. These studies reveal that existing alignment methods often focus on ensuring safety at the beginning of the text generation, which leads to a reduced impact of alignment as the sequence continues. Our research aligns with others that aim to minimize potential harm throughout the entire response sequence, rather than just at the initial tokens. Lastly, we differentiate course correction from existing self-correction techniques, which typically involve regenerating outputs. These methods require models to review and revise their outputs after generation, often through reprompting or by controlling each step of the decoding process. The drawbacks of these methods include the need for extra tokens during reprompting or the time costs associated with controlled decoding. An ideal course correction strategy should enable models to self-correct independently, removing the need for external prompts and streamlining the correction process.